Now what we're going to talk about are amines and amides. Now, a methylamine essentially is an ammonium molecule in which you have a methyl group attached to the nitrogen. So any amine means that you have nitrogen to which some carbon group is attached. And this right here then becomes, if one of the hydrogens is replaced with a methyl group, it becomes methylamine. If two hydrogens are replaced by methyl groups, this becomes a dimethylamine. And then the most you can have is a trimethylamine, in this case right here, where all three of the hydrogens have been replaced by a carbon radical. Now here what you have is a structure where the carbon in a benzene ring is replaced with a nitrogen. You still have the resonance there, but you have an extra pair of electrons here. And this right here is a pyridine type of structure. DNA consists of amines and carboxylic acids and are arranged as follows. Okay, so your tyrosine, all these different ones. They have nitrogenous bases associated with them, and those help link the things together in this type of manner. Now, we know that ammonia in acid will create the ammonium ion, NH4. Likewise, methylamines, or any of the substituted nitrogens, can also form methylammonium ions, or the dimethylammonium ion, or the trimethylammonium ions. Okay? There's a lot of important structures from that have amines on them. Right here you have a nitrogen in this sort of a five-member ring with another methyl group off of it. This is the formula for nicotine. Morphine also has a nitrogen and has this type of a structure. Codeine, a very similar structure over here. As a matter of fact, you can see the differences between these are this OH here and this OCH3 here. So that's essentially the only difference between morphine and codeine. And then if you talk about heroin, that has an O, and this C right here becomes a double bond O, so you have a ketone group out here, an ester. Actually, this is an ester because you have CHOO. So you have an ester formed here, and then instead of just an OH here, you've got an ester formed here as well. So two esters replacing this and replacing this are the only distinctions between heroin and codeine. So you see those slight differences. And that's what I had hoped for you to, that I'd wanted for your discussion way back when we had the lab talking about these different types of structures. But these are nitrogen-containing compounds, and many important pharmaceutical products have nitrogen in them, and the poppies. Now, one of the key things is that the smell of an organic molecule can tell you a lot about it. And when you pump gasoline, you know how the type of smell that you have from it. Though it's a very low hydrocarbon type of smell. And I've already mentioned about esters, the very pleasant fruit smell that they have, or the honey smell, or the mint smell. All those are esters. Okay. Now, the organic acids, they have a very different type of smell. They're very pungent. By the way, don't go smelling ethers. Smelling ethers is a good way to knock yourself out. But organic acids have a very pungent smell. Lactic acid is the sour milk smell. And that's also what is produced when you overexercise and don't have enough oxidation in your as you are overexercising your muscles. Two other ones, low molecular weight ones, are the caproic acid and caprylic acid. These are associated with barnyard smells. The capro, this part right here, comes from the Latin word for goat, and this is the worst possible goat smells are of that variety. Now, if you wanted to look at the actual names of those, this right here with 4, 5, 6 of them right here, right? That's 6 carbon atoms, and so that would be hexanoic acid. The caprylic acid, the other name for this was 6, 7, 8 carbons here. This would be octanoic acid. Okay, so these fairly low molecular weight ones have very, very rancid smells. Now, amines, those low molecular weight ones, if you have a diamines with like this one right here, this right here, it would be 1,4-diamino butane, right? 1,4-diamino butane. And that right there is, but its other name is putrescine. And you can imagine what that would smell like. This one right here, they named this one cadaverine, okay? The scientific name is 1,5-diamino pentane, right? But the more appropriate name, and if you are involved in working with body recoveries or decomposing animals of any type, these will be the smells that you will have, and they will be with you forever. Mercaptans. This ethyl mercaptan is appropriately named stench. Okay, this is ethyl mercaptan right here. So this would, if this is a thiol group here, so this would be ethane thiol or ethyl mercaptan. This right here is meththiol, and so this is methyl mercaptan. And these compounds right here are very useful, and they use these as very, very, very small concentrations are added to natural gas and other gas products, so that if there is a leak, you can tell it very easily. The skunk smell falls into the same category here. It's 1-butane ethiol. So it's C4H9SH is the skunk smell. So these three, the organic acids, amines, and mercaptans, are ones you really, you're not supposed to be smelling chemicals, but these right here, you're gonna smell them if they're present in any concentration whatsoever. Try to keep to these up here, okay? They are extracted from natural products, and they are wonderful. Now, right here, this is amines we talked about. These are amides. Amides means that you have the carbonyl group attached to that nitrogen instead of just a carbon. Okay, so this one right here would be acid amide, right here. So you have the carbonyl attached to this one right here, and this right here is hexanamide, right? Because it's whatever is attached over here gives it the name, and then this right here just becomes the amide portion of it. Okay, and so, and these can have other substitutes on them, either H or R for a carbon compound. Carboxylic acid, if you react it with an amine, will give you an amide. Okay, and whether plus water. So this is the typical way in which an amide is formed. So carboxylic acids are important compounds, as are alcohols, for starting materials for a lot of other materials. The other one, of course, are the halide versions of these when you want to add a specific component to one of those to one of those materials. This right here is the condensation reaction that forms to form a peptide bond. So there are approximately 22 different amino acids that are naturally occurring. And all of them have the structure where they have an amine group and they have an acid group. Okay? And depending upon which ones they are, they will react together and form a peptide bond between them. And you can see that you still have the carboxyl group out here, and you still have amino group out here. So you can have just very long chains of these. Longer chains of these make up proteins. Proteins that are either enzymes or constituents for growth. So the amino acids make up the polypeptides. The polypeptides make up the proteins. And this right here is a computer model of an enzyme, phenylalanine hydroxylase. And this is what a defect of this right here causes to lose its function, so it can't break down phenylalanine. And for people who have a problem with this right here, those are the only ones who would have a problem with the sweeteners that are used in most of the sodas. This right here is the basic element. This repeating element right here is one that you can see N means that it's just polymerized. And from this base unit right here, you get Kevlar. And this right here shows how it links together and why it is so strong. So you have the resonance bonds here. You have the hydrogen bonds formed here. And so it's a three-dimensional structure that you get for a very, very strong type of polymer. And just different uses for those. This slide right here has all the different types of materials. And what an alkene is with a double bond, alkyne with a triple bond, alcohol, the ROH, the ether, RR with an O in the middle, aldehyde with the carboxyl group here, ketone, carboxyl with carbons on both sides of that carbon, carboxylic acid, where you have in the carboxylic acid, there is some dissociation of this one. This hydrogen-oxygen bond is not at all like this one. This is a covalent bond strictly. This one right here, to some extent, is ionizable. And so that's why this is an acid and this can dissociate. Okay? And this right here is an ester, where instead of the H there, you have an O. And this is an amine, where you have the carbon group attached to nitrogens, 1 or up to 3. And then here you have the the carbonyl group here bonded to the nitrogen for the amide group. Okay? And these are examples of each one of them in terms of what their names are. And this is a very good table to understand and recognize what the different ones are, what their structure is going to look like, and some of their naming sequences. Now, let's go through some exercises. First of all, this right here is 1, 2, 3, 4, 5, 6. So it means it's going to be hexane based, right? But it's got a double bond right here, and it's on the second one. We start counting from this side. And so this will be 2-hexene, right? Here you have 1, 2, 3, 4, 5. So this will be pentane, and this will be 2-methylpentane, right? Okay, let's name some more. Well, this right here is 1, 2, 3, 4, 5, 6. So that's just going to be N-hexane, right? This right here, even though it's drawn a little bit differently, you've got 1, 2, 3, 4, 5, 6 again. And this is hexane the same, right? There's no real difference between these two. It's just the way that this last one has been drawn. This one right here, 1, 2, 3, 4. So we're talking about butane. And so this is going to be 2-methylbutane, right? 2-methylbutane. Now we have the triple bond here. So we start counting from here, right? So this is 1, 2, 3, 4. We've got a fluorine group there, right? So this will be 4